Language models predict tokens. They generate text. But text, on its own, cannot run a server command, modify a file, or execute an action in a real environment. To bridge this gap, the industry default is straightforward. Put the model behind a chat interface and hand it access to API keys. A chat interface is a communication layer. It is not an operating system. It cannot directly spawn a native process on a server or manage a real terminal session. In this standard chat wrapper architecture, we see the immediate danger of the setup. When the system tries to manage multiple agents concurrently, it creates disorganized nodes. Child tasks spawn and detach, becoming orphan processes with no termination mechanism when a script fails. What is missing is a true execution engine, a bridge that converts generated text into managed operating system-level commands. That bridge is ParviClaw-core. Built in Rust, it is a multi-terminal control plane engineered specifically to replace the chat wrapper entirely. We are going to map exactly how this system takes raw output from a language model and transforms it into native, cryptographically governed system actions. Deploying autonomous systems fails when organizations confuse generating text with executing code. Real enterprise deployment requires an architecture built for absolute operational control. Right now, enterprises are locking themselves into specific proprietary models, betting their entire infrastructure on a single intelligence provider. ParviClaw-core takes the opposite approach. On the right side of this architectural flow diagram, we see 3 distinct input nodes representing different language models. They all route into a single central gate, the ParviCore CTL binary. This Rust binary acts as an absolute boundary. Intelligence generation happens on one side, actual system execution happens on the other. Operationally, this means an organization can swap Claude for Gemini or GPT on Monday morning without rewriting a single line of their execution or governance pipelines. The control plane treats all incoming commands identically, no matter which model generated the text. By forcing all outputs through one standardized checkpoint, security teams can inspect and gate instructions before they ever reach the server environment. Decoupling the intelligence source from the execution engine prevents vendor lock-in. It ensures that as underlying models evolve, the rules governing their behavior remain entirely constant. As the diagram expands to the right, the central binary projects 3 isolated container zones. These are pseudo-terminals, or PTYs. Unlike a simulated command line inside a chat window, a PTY is a genuine interface to the operating system. This allows agents to execute real commands in real environments. Here, a master session within one PTY autonomously generates 2 dedicated child nodes. Structured data flows directly from the central binary to assign them parallel tasks. The control plane then injects specific execution commands straight into those active running worker sessions. As the worker executes the command, it produces an immediate feedback loop, returning state data and terminal output back to the control plane. Autonomous agents frequently fail by entering destructive loops. When that happens, the system responds instantly. Notice the active child node turning red to indicate a runaway process. The central binary sends a hard termination signal, immediately deleting the node and isolating the threat. Because this termination happens cleanly at the operating system level, it prevents cascade failures and eliminates those orphan processes we saw earlier. Managing this exact lifecycle, spawn, inject, return, and kill, reestablishes direct administrative authority over autonomous actors. Safely deploying AI depends entirely on the ability to cleanly and instantly sever its access to the operating system. When a terminal session is killed, standard flat logs are often lost with it. Even if they survive, they can be easily edited or overwritten later. ParviClaw-core defines any significant event, a session spawn, a command injection, or a process kill, as a material act. The system intercepts every material act. Watch the action packet drop from the PTY layer into a structured database. A digital signature locks onto the data block, mathematically sealing it before the action is ever executed. This creates a cryptographic leaf, a signed, non-editable record of the exact action taken. The diagram shifts to show them forming a horizontal chain. Each leaf receives a sequential number, linking it irreversibly in a structured ledger. From this ledger alone, an administrator can reconstruct the entire lifecycle of an agent session with perfect technical accuracy. This architecture eliminates the need to investigate what an agent did after a failure. The proof is already established in the math. Executing code without cryptographic proof is an unacceptable liability for any enterprise. By structuring actions into a tamper-evident ledger, those actions become verifiable assets. This tracking stems from a tester's mindset, the assumption that infrastructure will fail, and the system must be engineered to handle it. Expanding the ledger downwards, we see a dual-write architecture. One path writes to a local SQLite database, the other to a remote server. This remote path provides external redundancy. If the connection to that remote server breaks, the execution layer doesn't crash. A degraded status tag appears, while data packets continue appending locally without interruption. This is the principle of honest degradation marking. A secure system must clearly signal partial failure rather than masking it behind a false status check. Reliability also requires human oversight. Certain high-stakes material acts require human authorization before they can ever execute in the terminal. Through a human-in-the-loop export feature, a pending command is paused. An administrator reviews the action and promotes it using a mathematically signed token. True control over autonomous systems requires engineering explicit boundaries, where human judgment supersedes AI intent. Taking a macroscopic view of the completed architecture, the closed loop becomes clear. Intelligence flows from the models, funnels through the Rust control plane, executes in native operating environments, and is permanently proven in the cryptographic ledger. This rigorous structure directly addresses global AI regulation, where the European Union AI Act is setting a new, unyielding baseline for enterprise compliance. Regulators now demand that organizations mathematically prove exactly what their AI did, why it made those decisions, and that it operated safely. Companies relying on standard chat wrappers will be forced to retroactively bolt logging tools onto their systems, trying to reconstruct actions from black boxes. ParviClaw-core satisfies these strict regulatory audits natively. The exact evidence auditors require is generated contemporaneously with the execution itself. In this architecture, compliance is a natural consequence of correct, transparent engineering. While the rest of the industry races to sell simple access to rented intelligence, ParviClaw-core provides the engineering required to exercise absolute verifiable control over it.